Hello everyone, in this video I am going to demonstrate a Colpitts oscillator. As you can see, this is the view of my layout. You can see here this is the main oscillator with the transistors. Here you can see two BC547 transistors are used in a Darlington configuration. These are the biasing resistances here you can see, and here also this is the emitter resistance. These are the coupling capacitors, these three capacitors, these are the coupling capacitors. And this is the load resistor. The output is taken across this load resistor. Here you can see these are the two capacitors. You can see 0.1 microfarad, 104. You can see. So these are the two capacitors, and this is the main oscillator element. This is the main coil. And here you can see this is the RF choke. This RF choke is functioning as the blocking device for the high frequency. This oscillator is going to oscillate at a frequency of 35 kHz. So this 35 kHz frequency should not flow back to the power supply. That's why this choke is blocking the high frequencies from here to flow towards the power supply. In other words, this choke is responsible to maintain pure DC supply towards the circuit, and it will be blocking all the AC components towards the power supply. So this is how the layout looks like. This IC is not in use. I have just kept it there as it is. I have not removed it. These are the oscilloscope probes you can see here. So this is how the layout looks like. Let us discuss. First we will see the output frequency and the output voltage. As you can see here, I am getting a voltage of 36 kHz. This oscillator is oscillating at a frequency of 36 kHz. You can see here. And here you can see the duty cycle of the waveform is 48% and the voltage is 1.7 volts AC, 1.8 volts, nearly 1.8 volts AC. So now here you can see the frequency is 36.79 kHz. So this is the layout. So let us look into the waveform first, then I will be describing the circuit diagram. So here you can see this is the output of this oscillator. So if I reduce the time scale, you can see this is the wave. So if I zoom this waveform further, you can see I am getting a very nice sine wave. This is a very good sine wave oscillator. You can see here very nice sine wave I am getting. So here if I reduce the timing little, so this is the waveform. You can see. So if we see here, this is the frequency the oscilloscope is getting. You can see 35 kHz. It is little 35 to 38 kHz. It is little oscillating. So here you can see this is the waveform. So now I am going to describe the circuit. So as you can see, this is the circuit diagram. Here you can see this is the RF choke. This is the RF blocking choke. So whatever high frequencies are generated here should not flow back to the power supply. My power supply is plus 5 volts DC. These are the biasing resistances you can see. This is the connection of the two transistors BC547 connected in Darlington configuration. You can see here. So I am using here 10K, here 4.7K, and at the emitter 1K each. And here is 10 microfarad 63 volt coupling capacitor, AC bypass capacitor. This is AC bypass capacitor. And here is the coupling capacitor of 10 microfarad. And here is the coupling capacitor for the output. The output is taken across this resistor. So this is the load resistor. Let me write it here. This is the load resistor RL. This is the load resistor. So from here out. So like this the circuit diagram looks like. So now I am going to explain the circuit diagram further. You can see from the base there is a feedback loop connected between the collector and the base. You can see there is a feedback loop. So in this feedback loop you can see there are two capacitors C1 and C2 connected in parallel with a coil. You can see, so this is the main Colpitts oscillator element. So from the output, a fraction of the output I am feeding to the input. You can see a fraction of the output is fed to the input and it is continuously oscillating. So this C1 and C2 I am using 0.1 microfarad capacitor, and this is my coil. I am using a ferrite core with 14 turns of wire on the ferrite core. So let me show you the coil again. You can see this is the coil. can see this is the close view of the coil. So on this ferrite core I have wound 14 turns of copper wire. You can see. So as you can see here, this is the total Colpitt's oscillator circuit diagram. So this is the complete circuit diagram. So now let us calculate the inductance of this coil. Because we know we are generating a frequency of 35 kilohertz, so we will be measuring the inductance of this coil. So here you can see the capacitance C equals to C1 C2 by C1 plus C2, because these capacitors are in parallel when they are on a high frequency circuit. So if it is a short circuit, it will be like a parallel. It will be like parallel. Okay, both will be like parallel. So here you can see if we calculate, the total capacitance becomes 0.05 microfarad. Our frequency of operation is 35 kilohertz. So if we derive the formula, the inductance L equals to like this. This is the formula. So when we solve these equations, we are able to find out the L is 414 millihenry. The inductance is 414 millihenry. So this coil is 414 millihenry, and these two capacitors C1 and C2 are 0.1 microfarad, and they are generating a frequency of 35 kilohertz. So this is the Colpitt's oscillator I have made. So this is the first oscillator I have made. So here this is the circuit diagram. So in the next video, I am going to improvise this circuit for higher frequencies. Thanks a lot. Thanks for watching.